What we're going to do is we're going to make the line 16 here, the def compute Julia. We're going to give it some default arguments so that it just works out of the box. Okay. So we're going to give some default arguments to bound, lim, and cutoff. So if you set bound equal to 2.0 or 1.5 actually. Yeah, exactly. So Julia pure Python, just whatever default arguments are defined there in line 15, just redefine those inside of Julia Cython.pyx on line 16. Okay. Lim is going to be 1000. And cutoff is 1e6. So UI is still complaining? No? Okay, so the timing version worked, but it's a different issue with the UI now. Okay, so you're going to need to be using either Anaconda or EPD, Canopy or EPD to make the UI of this work, or you're going to need to install Chaco to use this because that's what's using for the UI. Okay, and Chaco will use traits and all that. So if you have your own installation that's not using Anaconda, if you're not using Anaconda or Canopy, then you're going to need to either pip install Chaco or easy install Chaco, one of those two. So the Julia UI just, no, it's not good. So despite appearances, I did test this significantly. So I apologize for the pain that this is causing people. So, and I wanted to give you this really nice kind of like application that you're speeding up, right? It feels like, okay, this is not some trivial thing that you're working on now, but it's a bit more complexity than I probably should have taken on for a tutorial. So, but hopefully the timing.py is working for most people. So that at least is a backup that you can use for just testing this out. All right, so in the last 10 minutes here, let's go through the actual steps of the exercise here in a bit more detail. So, so I have no qualms about just showing you what you're supposed to be doing, because if any of you ever used or come across the Learn Programming the Hard Way series, where they just tell you what to type in and you type it, I actually think that's a fantastic way of learning a programming language, because you're just getting experience with the language and you're running it and you're figuring out why doesn't my result match the result that this tutorial is giving me. Right? And it's not about necessarily all the thought, like you're still in the learning mode and getting up to speed on things, so it's perfectly fine just to take example and just add to it as you go, as long as you're doing it, as long as you're typing it in yourself and getting experience with it that way. So what we're going to do is we're going to take our Julia Cython.pyx file, and we're just going to add typing information and other things to speed it up incrementally. Okay, so I'll do that with you, just in the interest of time as well. Okay, but please join along with me. So let's look inside of Julia Cython.pyx, and we have three functions: ab square, so this square the absolute value of our complex value, kernel, and compute Julia. So the first step is we're going to be adding lots of floats and ints. We're just going to be statically typing our scalar variables, or scalar inputs, that sort of thing. So let's do that. And I'm square. I'm going to add a float here, a float here, inside of kernel. Bunch of floats here. It's a float, and cutoff is going to be an int. Okay. All right, and then down here, compute Julia has, I'm sorry, what? CDEF count. Oh yeah, you absolutely can. I'm just going directly from the slide is, but if you want to count a CDEF int, go for it. We'll do that in the next slide. So here are a bunch of floats inside of compute Julia. And bound. Okay, so just taking the slide information, slide 45, putting those types into my source file here. And of course, there's a solution file if you want to pull that open. And I think it's just so long as you're doing it yourself and going through this process, even if you're pulling it from an existing solution, that's perfectly fine, right? This is not being graded. Right. If so, the only function that needs, well, compute Julia is called from other Python code. Right? So that has to pull out all these Python objects and pull out the floats and the ints from these Python objects. Right? So there's unboxing going on there. But what we want is kernel is called only by compute Julia. It's not called by other Python code. So we want kernel to be a fast C function. And if you look, this absolute square function is called by kernel on this line here. So we want that also to be a fast C function. Right? So, but compute Julia is going to have to do unboxing. These other functions, though, we don't want to have to do any unboxing at all. We want to keep it all at C level. So here, use called timing. No. Why are you complaining? Here we go. Sorry, my bad. Sorry. So cutoff. Apparently, we're trying to pass in a double to cutoff here. Sorry. That worked better. Okay. So, typo here. Cutoff needs to be a double or a float for this to work. So again, here's my source file. I urge you to copy these contents here to make things work. So we have all our arguments are typed now. In absolute square, and kernel, and compute Julia. Some of them take default arguments, like in compute Julia here. All right, so now we're going to turn our attention to, well, the next step is pretty simple. We're just making our absolute square function a CDEF function, which returns float, and our kernel function is a CDEF function that returns an int. Okay. So absolute square is going to be a cdef float, absolute square, and then kernel is going to be cdef int kernel. Okay. So we're still just at the function interface level, but since absolute square and kernel are called only inside of the Cython source file, we can make them cdef functions, and so there's going to be 0 Python overhead when calling them. Okay. So give you a little bit of time to work on that. And try to run timing again. Should recompile and should hopefully notice a fairly significant speed up by now. Before it was 6.7, now I'm down to 0.1 seconds. Okay. All right, you keep on going. Oops, my bad. So let's go into the function bodies and type the local variables. So absolute square, absolutely everything is typed now. It's a very simple function. There's not much to type, but it's pure C function. Everything's typed. Let's look at kernel. So someone suggested typing count. We can type that as a cdef int count, and then we can cdef float lim square. And the reason we're doing this limit squared stuff is so we can avoid calling a square root all the time for this. We're going to get the same result. And let's see here. I think everything inside of the body of this while loop is now typed. ZR, ZI, CR, and CI, so it looks good.
Could you have done cdef colon there?
Oh, yeah. Yep, let's do that. So oops. So you can do this, where you cdef colon and then in an indented block, you just declare things as if they were in C. That works as well. Okay, so I think that's everything typed inside of kernel now. So we expect a speed up from that. And now down here, we can type a few things as well. Let's see, Julia and grid are NumPy arrays. We're going to leave those to the next step. But we have some variables I and j and x and y. So let's type those. So I can say cdef, say int I and j, and I can say float x and y. So that's typing our loop, some of our loop variables. We still have to type grid and Julia. We'll see how to do that next. Okay, so that's typing our internal variables now. So let's see what difference in performance that gives us. So now we're down to, what, 20 milliseconds or so? Before we're in like the 100 millisecond range. So another factor of 4 or 5 or so boost. So that's pretty good. Okay, so now we can use our typed memory views for declaring our arrays, Julia and grid. So let's use that. We're going to do it the way we have it here. We want them both to be C contiguous so that we have better performance when we're iterating through them. And Julia is going to be declared this way and grid this way. So down here in compute Julia, I'm going to say, let's see here, int colon 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 1 Julia, and then float colon colon 1 grid. Okay. So that's typed, I believe, everything except T0, but that's not terribly important since it's outside of our for loop. Okay, so we typed our memory views now. Let's time it again. Uh-oh. For D-type mismatch. it's unsigned, I see. Try this. So I had an error before. Since this is declared as a uint32, we need to have Julie declare this buffer declared as an unsigned int. Okay. So I'll just show you this, and then we'll wrap things up. Okay, now we're down to the 6 or 7 millisecond range. So before it was about 20 milliseconds or so. Okay. All right, so that gets to basically where I wanted to get. I wanted to, well, I would have loved to be able to get to the pulling in P range and pulling in OpenMP to parallelize this loop even further. We can get another factor of 3 out of this or so. But don't have time for it, so I'm gonna have to. It is in the slides actually, and there's a little bit more in the slides as well about Cython directives, that sort of thing. I have to refer you to the Cython documentation on that. This is the parallelization stuff you would do to use P range for a parallel version of range that uses OpenMP under the covers. Okay. So we saw the original version was about 6.7 something seconds. Now we're down to 6.7 milliseconds, right? So very clean factor, 3 orders of magnitude speed up over the pure Python version. Right? So I hope you had some success with this capstone exercise. It at least gives you something to play with and work with. And encourage you to take this, look at the solution as well, because that's much more fully worked. And a lot of the pieces are there for the process for speeding up Cython code. So just one more slide here to wrap things up. So I just want to talk about Cython in the age of Python JIT compilers. Right? I'm sure a lot of you are very excited. I am too about NumPy, which is having some amazing results. I'm sure everyone here has at least heard about PyPy, and it's another JIT compiler. It's not focused on numeric code, so you don't get a automatic 100x speed up just by using PyPy on NumPy code, but it's more designed for general Python code. And they're definitely on the scene, and they're making great strides very quickly, and I think it's fantastic. And so the great thing about JIT compilers is that it's all dynamic, right? In Cython, you have to statically declare types. And there's some flexibility there. I didn't get into it. You can use these things called fuse types in Cython, but you still have a lot of static declarations. And so that can be a little difficult when you want to support multiple versions of a function. And NumPy is often on par with Cython code like we saw here, and with significantly less work even. So why still use Cython when you have these sorts of things out there? Well, there's still some reasons, and I think Cython will be around for a long time, even with these JIT compilers coming on the scene. As we saw earlier, Cython is part of some major projects that we're using as part of the scientific Python stack. And it's often much easier to have a application level programming in C extension modules using Cython rather than depending on external stuff like JIT compilers, which often have a lot more dependencies to get them working. So you don't have to have Cython installed for your users to use Cython code. Cython has a lot of mature wrapping and diagnosis capabilities like Cython.a that JIT compilers lack. Cython gives you a tremendous amount of control while being very flexible and high level at the same time, which is really nice. That's one reason I really like it and why I imagine it'll be around for a long, long time. Cython can speed up both general Python that's not specifically NumPy stuff and also numeric code at the same time. So it's kind of has its foot in both camps. And also Cython gives you this very easy way to pull in parallelization support using P range. I didn't get to cover that, but it's not hard at all. So Cython's still going to be around for a long time, and but I imagine things like NumPy will probably become the tool of choice for speeding up numeric code, just because it's so easy to do. Anyway, that's all. Thank you.